The second part of Einstein's theory of relativity, called the theory of special relativity, addresses the strange case of the speed of light, the fact that the speed of light is independent of the motion of the observer or of the source of the speed of light. So in this little illustration here, we see a flashlight moving toward an observer with a velocity v, or the flashlight moving away from the observer with a velocity v. In each case, the light moves forward at the speed of c, the same speed. It's independent of the speed of the observer. Regardless of the velocity of the rocket, an observer sees the flash of light pass her at the same speed, c. The speed of light in the examples we have here. If you move with some velocity v, then associated with u is a gamma factor. This gamma factor, given by this equation, depends what your speed is. V is your speed. So for example, if you are not moving, and your velocity is 0, v is going to equal to 1 minus 0, which is just 1. V will equal 1 minus 1, 1 minus 0, which is 1. You have a gamma of 1 at that speed. The faster you go, the bigger the gamma becomes. And of course, gamma can never get to be c, because if v is equal to c, then you have 1 minus 1, which is 0, and 1 divided by 0 is undefined. If we look at this chart on the left here, we see what gamma is for various speeds. For example, if you are moving at 1/10 the speed of light, gamma is approximately equal to 1. But as you move faster and faster, then gamma gets bigger than 1, and as you approach about 90% the speed of light, then gamma is higher than 2. As you get even faster and faster, you can see gamma gets bigger and bigger, and it approaches infinity. As this graph shows you, gamma approaches infinity as you approach the speed of light. We saw that one factor in Einstein's theory is the only way the speed of light. So let us consider the example of two twins. One twin leaves on a trip in a rocket, during which time he'll be traveling for many years near the speed of light. When that twin returns, the other twin has now aged a different amount. Let's look at this from a problem perspective. Let's consider the following problem. The twin is traveling to another star which is 10 light years away, and he's traveling at 80% the speed of light. First of all, let's answer the question, what inside that rocket ship, what is his gamma factor? If we look at the chart on the right, we will see that at 80% of the speed of light, gamma is 1.67. So the gamma factor is 1.67. First of all, let's calculate how long does it take him to get there and come back, traveling at that speed, from the point of view of somebody from Earth looking at his trip. Well, his velocity is equal to distance divided by time. But the distance we're going to use here is 10 light years, and the time is 0.87. The velocity is 0.8, the speed of light, 8/10 the speed of light. So from the velocity equals distance over time equation, the time is equal to distance divided by the velocity. It will take each part of the trip will take 12.5 years. That means 12.5 years to the star and 12.5 years back. But what is the time elapsed inside the rocket? Well, inside the rocket, the two times are related by gamma. So the time inside the rocket, which we have called the proper time, will equal the time outside the rocket, which is 12.5 years, divided by the gamma factor. So it'll be only 7.5 years. So the round trip will be 7.5 there, 7.5 back, 15 years, as opposed to 25 years.